Hi, everybody, and welcome to Astronomy 120. This is the late start class. It starts actually it started yesterday, but yesterday we didn't really have any sessions, so we scheduled it for Monday, Wednesday. So this is our first contact for this class. We have to talk a little bit about this class. We have to talk about the format for this class. And I know some of you are sitting in my astronomy class. I mean, the other astronomy class, the 125, which is the lab version of this one. And so this is the lecture part of that. And we have to go through the introduction of the class and basically the materials that we're going to be covering in this class. Because it's a late start, so a little bit of fast-paced, compared to the early start class we started about 3 weeks ago. So there is a little bit of time difference in here, okay? So we need to cover a little bit more materials in the same span of time, basically, or at least the span of time, I should say. Anyway, the point being is my name is Bouzidi Jumway. I'm going to be your instructor for this class in astronomy for this fall semester. I've taught this class before, and actually I'm teaching it right now also in the same place. So I have experience in that. My background is I have a PhD degree from the University of California, San Diego, UCSD, in physics. And I taught physics and astronomy here and there, basically, but I taught a lot, especially in the district in Crafton. Now I'm basically fully dedicated to Valley College, so that's basically all of my classes where they are. Currently, I'm teaching physics and astronomy in Valley, and that's the only basically stuff that we have. But I have a lot of classes in this place. Anyway, so this is a little bit about me, and what I'm doing, but let me jump into the course so that we see exactly how it looks like so that you guys have an introduction of it. The biggest question that, at least early on, a lot of people sent is about this live sessions. Do we have to attend live? The answer is no, you don't have to attend live. However, if you cannot attend live, you really must watch the recordings then afterwards. Here is how the process works. Once the recordings are made available to me, what I do in this case, I go see if there are some minor changes to them. I fix them a little here and there, and then I post them to my YouTube channel. After they're basically cleared the YouTube channel and they're fully uploaded and everything looks good about them, then I come back to Canvas and provide a link to those videos so that you can go and you can watch them on Canvas. The video title will have the following words in it, starting every video for your class. If you don't see that starting words, that's not for your class. And the words are Astronomy 120-71. In other words, your class. You don't see that in the posting, you don't have to watch it. So it's critical to watch all of the 3 words. If it's a physics or something else, you might just skip that. If it's another astronomy, you have to pay attention to the next 2 words because there is another Astronomy 120 going on right now, and it posts its recordings on a regular basis, but that has a -70 on it, okay? I mean, you're welcome to watch it if you want to, there is no harm in it. But to be focused on your class, it will have the -71. Which brings me to another important point. You can go and subscribe to the YouTube channel. And also the titles are clearly there too, so that you can see which portion you're focused on. You can subscribe to the YouTube channel at least during the semester. When the content is available, YouTube will notify you and tell you, hey, there is a new content that is uploaded. Once you see that, and it has the 3 conditions, it has to be in astronomy, it has to be 120, and it has to be 71, then it's your class. That is the one that you're going to focus on. Anything else, you may just basically not focus on it because it's not your class at that point, okay? So, if you can attend live, that is the best way to do it. You have to do that as much as you can. It enriches the topic. It brings you into the live session. If there is something that is not clear, it will be clarified, okay? And it enriches the topic. In other words, the topic can only be better by you being present and asking the questions or reacting to it or letting me know how things are going so that we can fix what needs to be fixed, okay? If you are watching it recorded, yeah, first of all, you have to allocate time for it, okay? So if we have an hour and a half or an hour and 40 minutes to go through the lecture, you must allocate the same amount of time at home to do that, okay? And take notes. If you sit down and watch it on YouTube on your phone, I can do an hour and a half. I cannot do probably 20 minutes. It's too much, tiring. But if I'm seated in front of the screen with my notes on and following the discussion, taking notes, oh, this is important, so I'm going to take notes. Even if it's not important, I'm going to take notes. It keeps me on track, keeps me focused, and as if I'm in the classroom, because that's exactly what it's supposed to be. Because when you come to the classroom, you're going to dedicate an hour and 25 minutes or 30 minutes or something, sitting in the instruction in there, getting the feedback from your instructor, from your peers, and you're giving feedback to your instructor and to your peers and interacting with the content until you leave, everything is fully done. Think about it this way too. Now, while you're watching the recording, you might come across a question that you might have that is not clear and nobody asked it. Or it might have been asked or discussed, but it's still not clear. Then in that case, it's a good idea to make a comment in the posting in there, or to send a request, to send a message. The reason why I'm saying it's a good idea to make a comment or to go to the discussion and post it there, because you might receive a feedback from your peers, which is very helpful, which is probably sometimes far more helpful than what the instructor gives you. And then the other thing also, your insight will be very useful and helpful to other people, because sometimes other people will miss the points and think that, or don't even think about it. It's not ever cross anybody's mind, including myself, but it comes across you and everybody benefits from that. So it's a good way to follow those lectures as if you are in the classroom. Allocate the time, the space, and the conditions for it in such a way it's not tiring, and it's not making you sleepy, and you focus and you benefit from it the maximum, because it's still a class after all. It's not a movie or something to be entertained with. So there is some learning that needs to happen and some interactions, a level of interactions that need to occur for it. Okay. So this is in general. Okay. So let me introduce the class to you. I know that you have access to Canvas. Some of you already have done that. Before I do the sharing, let me make sure I'm in the proper view, because sometimes, and not sometimes, I always have to make sure that I'm looking at it from the vantage point of a view. Okay, so I'm going to go home and I'm going to change the view to student view. Now I can share it with you guys. So share screen. Okay. So this is how the course looks like to you when you first come into it. Okay. This is the home page. It has a lot of stuff in here, a lot of content in here. A lot of it is actually coming from the syllabus, at least these pages are. So if you go to the Canvas, it's going to take you to the information that are in the Canvas. If you go to the accessibility, actually this stuff is gives you links also to resources if you really need help with that. Do not hesitate, take full advantage of it, okay? And the rules of how to communicate and so on and so forth, okay? So this is the landing page. Most of the times though, you will find yourself in the models link, which is this one. That is important. It takes me to where my content is, what I need to do on a regular basis. So most of the time, when I go to the home page, I click on this one, or I can find it in here. It's the same link. As a matter of fact, if you look at the bottom, if I let go of this, focus on this area where it says you are currently logged into student view, okay? If I hover over the models, it's giving me HTTPS, and at the end, the main thing to look at is /models. That's your class /models. If I come in here, this is the same thing. So I could go here or here, it should take me to the same place. And that is most of the time where I'm going to spend my time on. That's those two pages. Okay, so when I come in here, it has this general introduction video in here that talks about all of the classes that I have in general. And but this is basically specific orientation to you guys for how to use Canvas. Okay, at least for this class. Other instructions might emphasize on other things, but at least for this class. There is this thing in here, an open topic discussion. It's a good idea to visit it on a regular basis and also to post to it if need be, and subscribe to it, because that is where you go and ask general questions. It's not graded. There are no penalties for doing this. There are no, basically, it's just an open discussion. So to get things started with your peers and classmates, so that if there is a question, hopefully somebody will pick up on it and answer it in there. Okay, and it's open for the entire semester, this one. These are the syllabus. This is the electronic version, and this is the PDF version that you can print, and you already have received a version of that, okay? When you are on the landing page, it gives you shortcut discussion to these things in here. Oh man, there are a lot of things that I probably will have to streamline this thing in here, but the point being in here is, this is the welcome, that's a message. This is actually a message also that you should have received. Because I'm logged in as students, it's showing me even the messages. And this is a quiz that is part of the assignment. So it's giving me these things. Please do not use the to-do tasks in here unless you are really crunched on time and you don't have anything to do, but that you don't have a lot of basically resources, a lot of time basically, and you would want to get started right away. This is bad practice. Do not rely on the to-do. This is not how we do business. We have to rely on the models. Before I go to the models, let me discuss the syllabus a little bit because it's important. Well, this is our first contact. This is a purely online class because we're doing the Astronomy 120 is online class. And let me open go back home and open the PDF is better, okay? Because I think I need to fix some errors in there because it's copied it from somewhere. So I'm gonna open it and let me, do you guys see the syllabus in here opened in this page or not?
Yes.
In PDF? Okay, very good. Thank you, Gladys. Anyway, the point being in here is this is your syllabus for your class. It's the class meets on a regular basis, Mondays and Wednesdays at 10:40 live. As I was saying in the intro, you don't really have to attend that live session. It is extremely important that you attend if you can. Please do so. You are strongly encouraged. First of all, you put that in the check mark that you did that, because you'll be forced to attend the recorded session and to go and watch the recording session. And usually that's not as productive as attending live, okay? So you are strongly urged to attend live session. The format, as I was saying, is online. This is the regular stuff. My office location is actually PS 194, Physical Science 194. But it is really not ready yet. I mean, they're still working on it. And if you go there, you will see that a bunch of people still working on it. So right now, I meet with you guys online. If you need help, do not hesitate to send me a message. I will go through these times if need be, but these times are not written in stone. So in other words, we can find other flexible times for you, okay? Friday morning if nothing works, or Friday afternoon, for example, Wednesday afternoon. So if none of these times work for you, please let me know, and I'll be more than happy to accommodate. Now, if you have to be on campus and we are going to do things on campus, there is no problem with doing that. Even though I don't have an office right now, we can still meet in the STEM center. I should expect that this situation with the office to be fixed within a week or two at most, okay? So we can meet in the office. If not, we can meet in the STEM center. And the STEM center is a very nice resource for you guys anyway. There are a lot of offices in there that we can pick and basically go and discuss the grade, discuss the assignment, discuss whatever you need to help with. And then, as I was saying, but then the STEM center itself is a useful resource that you guys could take advantage of by basically, if you need help with math, if you need help with this class or any other class, they usually can, if they cannot help you right away. And most of the time they have tutors in place, but if they can direct you to the place where you can go and get the resource that you need. So take advantage of this. This is typical stuff. This is the content that we're going to have in this class. And this is the textbook. And a lot of you sent me messages about the textbook. This is the textbook, the printed version of it, okay? And you have the electronic version, which is given to you by the college to access it throughout the semester. So take advantage of it. I think it's called Brightwave. I'm not honestly well versed in this because this is new to me, but I know that the bookstore will give you codes or will give you basically access to it. And how you access it, it's actually in the syllabus itself. So if I go back into the syllabus, was it? Yeah, it's in here. It's in the last page. We're in the syllabus page. I thought I'm on the online, but it gives you the instruction on how to register. So you're going to go to McGraw-Hill Connect, and then you're going to look for this information, the instructor name, the section that you're enrolled in, and you probably are going to click on this link and it should take you right then and there, okay? But you need that code, okay? You need that code. Once you do that, you should be in good shape to access the class, okay? So this is the resources that you have, and some more resources in here, useful stuff. This is how the grading is going to be done in this class. So participation, assignments, homework and quizzes, and midterms, okay? The total grades is 100%, okay? So this is how, so you're asking me how am I going to do participation on online? Remember what I told you guys, that you have to watch the recordings or attend live. You'll be asked questions. You'll be asked also questions based on your engagement with the content. And those discussion items, those responses, they are going to be great toward your participation. So if you don't log into Canvas, if you don't do these assignments, your grade will suffer from this 10%. You're going to lose that, and you're going to be working off of B instead of an A. You don't want that, okay? So this is the general information about the course and basically what we're going to be covering throughout this units in here this semester. The book is divided into units so that you guys know. And we're going to start with units 5 and 6, and then we're going to move on until we cover all of the units, including the astrobiology. So what are the topics covered in this units? I'm going to give it to you in basically in a nutshell. Okay. So what we will cover in this topics, of course, is the universe, everything. And what is the universe, you ask? It's everything. So what are we going to learn? We're going to learn about everything. That's in a nutshell what it is. But of course, we have to approach it a little bit more in more scientific fashion. So what do we have? We have the solar system, of course, that we need to learn. And the solar system, it's made up of several components. The biggest by far is the sun. But the sun, we're going to leave it aside for a moment. It's a star, so we're going to serve us as a good thing. Here is the strategy, the plan that we're going to tackle with. If we want to study something, this is something coming from basically from the scientific methods, from physics to be more specific, okay? It's easier to make us, to study what is familiar, what you know first, okay? Based on what you know, try to build a model to understand what is close to it, and then expand your knowledge from that in that direction. That's easier by blocks. So if we're going to study the planets in the solar system, technically we should go to Mercury and study it, we should go to Venus and study it, then we should go to Earth and study it, then Mars and study it, then Jupiter, then Saturn, then Uranus, and then Neptune. Those are the 8 planets in the solar system. First of all, we don't have the resources to do that. And it's, if we could, we would. That would be ideal, but it's not possible all the time. So what we do in this case, the easiest one to study is Earth. We can try study geology, we can study its basically atmosphere, we can even go into the history of the Earth, and we can make basically models for how the Earth behaves and so on and so forth. Take that and extrapolate it toward the other planets and see if they make sense. Obviously, we're lucky enough to send probes and landers and orbiters to other planets. So based on what we know for Earth, we can take that and compare it to the other planets. It turns out the planets are divided into 2 sections. There are the inner planets, which are rocky, and there are the outer planets, which are gas giants, much bigger, but they are mainly made out of gas and other basically solid water and all of the other solid of the gas and liquid forms, okay? Anyway, the point being in here, icy objects, they're called. So these are the planets that we're going to study in the solar system. Then all of the planets, with the exception of 2, They are Venus and Mercury. The exception of these two have moons. So we need to study the moons. Again, the easier thing to do in this case is take our moon, which is close by. We had people land on it too. We had men mission to the moon. So we brought rocks from it. Based on that, now we have an understanding. It's close by so that we can look at it, we can study it, we can take as a sample for us. Then we try to make generalization for the other moons. It turns out that Earth's moon is an exception, given its size and its proximity to Earth and so on and so forth. But it serves as a good example to study the rest of the moons. Mars has two tiny moons that are most likely captured asteroids. And then you have the big moons of Jupiter, which are actually wealth of subjects. We're going to talk about them. We're going to study them in depth. And then we have the moons of Saturn, or I should say the moon of Saturn, which is by far the most important one, Titan. And then you have the moons of Uranus, which I'm not going to spend a lot of time on, but Neptune has a very interesting moon, Triton, which is actually a very important topic to talk about and see its peculiarity, because it sits really in an odd position, and we try to understand it because it gives us some insight into what happened to the solar system. So now we have covered two topics already from the solar system. Then there is another one, the dwarf planets, namely Pluto, Eris, Makemake series, which is not too far from which is between Mars and Jupiter. And then we have Quasar, we have Sedna, and other kinds of dwarf planets. So they are interesting topic by themselves, and there are a lot of them. Okay, so again, we're going to take the one that is familiar to us, namely Pluto, because we had actually a flyby by Pluto that gave us a lot of insight on its structure and so on and so forth, and most likely the others look the same. Okay. Now the solar system is not finished. We still have the asteroid belt where Ceres is, and where Vesta is, and other dwarf planets. And then you have the Kuiper belt, which is another belt sitting outside. And all of the structure is an amazing structure that we're going to study. So this is just the solar system by itself. This is not the entire solar system, though. Still have more stuff in it. We have the Oort cloud, and the Oort cloud and the Kuiper belt send on a regular basis those comets that come through on a regular basis in our night sky. So we're going to study that too. And that's basically in a nutshell what the solar system is without the sun. Then we're going to go and study the sun and what's happening in it, and how do we know what happens inside of it based on our observation and based on what measurements are on Earth. That's going to serve because we want to study all of the stars. We don't want just to study the sun. So the closest by object that we can take is the sun. Study the sun, we should know more about the stars in the solar system, in the galaxy. It turns out that the star can be classified based on their size, and the sun is just a typical medium star. In terms of number, it's actually not that medium, not that small, it's kind of big, but in terms of luminosity, in terms of size, in terms of age, in terms of all of that, it sits right in the middle of the range of the stars. You have some that are tremendous, I mean, much, much bigger than the sun. Some of them that are smaller than the sun, but even hotter than the sun. Some of them that are much bigger than the sun, but they're cooler than the sun. So they have they range in sizes and temperature and properties and what they emit and what kind of flares they produce and so on and so forth. And then depending on their size, they will have different kind of evolution. Some of them, they go through their life cycle very quickly, the big ones, and some of them, the smaller ones, like the red dwarfs and the brown dwarfs, they actually live a lot longer. They will outlive everything. Okay, so that's basically so the age of the sun is probably about 10 billion years, but that's an average. Okay, there are some that die within a million years, and some of them that can last for billions and billions of years, well past anything that you can think of. So those are the things that we're going to study. Then you have stellar clusters that we're going to study, group of stars like the Pleiades. For those sitting in the lab at Astronomy 125, we will have a full dedicated lab, actually 2-session lab just for it, for the Pleiades. There's the Hyades, there are all kinds of cluster of stars that we're going to study. And then we're going to study the galaxy itself and its main characteristics and the different kinds of stars that it can have, and the arm structure of the galaxy, and the fact that it's a spiral galaxy. And it gives us an insight of the local group of galaxies that we have in our region, because when I say our region, we're talking about millions of light years away, further than anything that you can imagine in terms of time and space. But the point being in here, this is our region. Our next door neighbors, the two Magellanic Clouds, are actually two independent galaxies that orbit our galaxy. And there are other smaller galaxies basically that orbit ours, so that they are satellite galaxies. Then there is a big neighbor, next door neighbor, which is about 2.5 million light years away from us. And that is actually Andromeda, which is actually much bigger than our own galaxy. And Triangulum, which is actually a smaller galaxy than both, but it's still a big one. And in our local group, there are some 50 some odd number of galaxies. This is our group of galaxies that interact gravitationally. Then after we move from our local group, we're going to study the cluster of galaxies. Our galaxy is part of the Virgo cluster, which is even a bigger group of galaxies. It expands so much in space that you cannot even imagine. Well, this cluster of galaxies, the Virgo cluster, is actually part of another cluster, which is the supercluster, the Virgo supercluster, where our cluster is actually enclosed in it. And the Milky Way is actually sitting at the edge of the supercluster. So our local group is not really in the center, but it's somewhere in the edge of it, because even that supercluster is part of a bigger cluster, which is called the Laniakea structure. Okay, so we're talking about unimaginable size in here for the universe. So we happen to be, it seems to be that the entire Laniakea, all of the galaxies, first of all, they arrange themselves in some sort of filaments, and between the filaments, those are made up of gas and galaxies basically, and then there are voids in between them. No galaxies or hardly any in between them. And all of them, they seem to be drifting in one direction into something we call the great attractor, where we don't even understand what's going on in that level. This is not the entire universe. This is just a huge structure that expands billions of light years, but it's not the entire universe. So the entire universe is even bigger than that, okay? And when we talk about the universe, we're talking about its size, which is an unimaginable size already. This is the visible universe. And then there is beyond that, there is the actual universe, which expands in sizes that are impossible even to imagine. Now, we're going to ask questions. Where did the universe come from? Where is the universe headed to? And we're going to answer those questions. Sitting in a very, very tiny rock in the solar system that is dwarfed by at least 4 big planets, by the sun that is dwarfed by so many stars in this region only, by the size, the sheer size of the galaxy, by the sheer size of the local group, by the sheer size of the cluster that we're in, by the sheer size of the supercluster. And we're going to ask a question, all of this, where did it come from and where is it going? And we're going to provide an answer. This is one of the most fascinating things that can happen actually that is actually amazing, that with limited stuff, with limited space, with limited time, because we existed, I mean, in a fraction of a fraction of a fraction of a second, but we're asking all of these questions. When I said we existed, I mean mankind, from the beginning up to this point. I don't mean human life, which is about, what, 60, 70 years on average, or maybe more, doesn't matter, 100 years, okay? So it's not long enough compared to the time scale we're talking about and the size we're talking about. We'll close this topic by asking questions about life outside of the Earth. First, in the solar system itself, and we're going to assume that life will take the same carbon-based form, which is not a requirement actually for life. Life could evolve in other conditions not based on carbon-based life like we do in here, carbon-based chemistry, like what we have on Earth. It could be potentially others, even restricted to this format, to this form. we will see that life, I mean, has plenty of places to exist, and the probability for it are endless. Okay. Outside of the solar system, of course, but inside the solar system, there are places that we can go and look. When we say that, usually we mean Europa, which is the smallest of the 4 big moons of Jupiter, and also the other 3 moons, namely Ganymede and Callisto. I mean, excluding probably Io, which is kind of hellish actually because of its high volcanic activity, and then also even hellish worlds like Venus. There are some discoveries in 19 or 17? No, 2019, where they discovered phosphine, which is an element in its atmosphere that is usually on Earth produced by life. But now there are some revisions of that. So even on, but it's probably in its atmosphere, not in its surface, because the surface of Venus is unbearable. We're going to talk about life in other places, like, for example, Titan, the moon of Jupiter. I mean, the moon of Saturn, I'm sorry. And even other places, actually just in the solar system. But then we have exoplanets, and exoplanets that meet the requirements like Earth does in terms of proximity to its star, in terms of the size of the star, because you don't want it to be too small, like Proxima Centauri, for example, the closest star by, which is a red dwarf star, but that flares a lot of radiation on a regular basis, and that decimates life if it is a carbon base like ours, near one of its planets, and we know it has planets. But we're looking for a star the same size of our sun, which is in a stable environment that can basically sustain life. Planets that are in the Goldilocks zone, that have the conditions right for life, and namely that water exists in a liquid form, and those are what we're looking for. And this is what the function of the Hubble telescope is. I mean, not the Hubble telescope, James Webb right now, is to look for signs of that, look for the chemistry in the atmospheres to see if life exists in those planets. So again, we're going to explore that. Part of the stuff that are going to be explored in this class. Sounds exciting, doesn't it? Yes? You guys excited, or am I the only one excited? Okay, thank you, Connie. Okay, okay. So we have a lot of things to talk about in here. So let me get into the. Let me make sure I didn't miss anything from the what I'm supposed to cover in here. Yeah, the other thing probably, and you already have it, is the announcements. Make sure that you check the announcements on the regular basis, and you'll be receiving notifications from me on a regular basis. So please make sure you respond to those and get them done and things like that. Anyway, so let me start with the first chapter of this class. But before I do that, there is a link in your I know for those who sat yesterday in the lab, they know about this, but those who are not, you really need to know this because it's part of our class also that we'll be using a lot. So let me go back into that share. I lost it. Okay, so let me go back into it and open it. If I don't open it, now it's open, so hopefully it's going to give me the link. Share. Okay, it's here. So again, part of the resources that you have is this Stellarium link. Okay, so I'm going to click on it. Once I click on it, do you guys see it? Stellarium?
Yes.
Yeah.
Okay, very good. Thank you, guys. Okay, so it's a nice software to have. It's a free software to have on your desktop or your laptop. That's a free 100%. You don't pay for it a dime. If you have a Mac machine, and if it's a 64-bit, you can download, I think if you have an ARM, say a 64, which is those small laptops that basically have limited capabilities in terms of software. But most of the time, you either have an x86 or an x64. So either one, it doesn't matter. If you have a Mac, and if it's not an ARM, you can download this, and you're going to be in good shape. So just make sure you download this, not this one, okay? This one is, there is an extreme condition. Usually those are the cheap ones that you have. And if you bought one of them or provided to you by the college, then you probably you're going to have that one, okay? For Windows, it's the same thing, but they are separate architectures. Anytime you download a 32-bit, it's going to work. It doesn't matter what the operating system is, what the system is. But to take full advantage of it, just make sure, I mean, if your computer is 64-bit, download the 64-bit, it's better, okay? But this one will work, should work, at least in the old days, it should work. Now, if you happen to have a Linux, then you know exactly what to do, because Linux is usually for people who have a kind of have a machine in their setting, which is, I think I have Ubuntu in there or something. So you can download one of these versions, depending if you're a programmer, probably download the source code and compare it to itself. In either case, you can still get this web version. Before you go to the web version, I actually happen to have the phone version. So I'm going to open it and I'm going to share it with you guys. The phone version is not free. The phone version, you pay for it like $5, or I don't remember how much I paid, honestly. I think I paid $4.99 or $2.99, okay? So either one, that's how much I paid for it. So you could do that, but what I found out is basically the phone version is just good when you are by yourself somewhere in probably in the mountains or near, I don't know, what is that, Joshua Tree or something, and you need to look something quickly, you could do that. You could use the phone version. But it's better than the one that comes with the phone. I know there is a Google one or there's an Apple one or something, but actually it's better. It gives you far more information on the object you're looking for. There is the web version, and I believe the web version is the phone version. And the reason probably they make you pay for it is probably to raise a little bit of money, but actually to pay for the hosting of this code probably and on the somewhere basically where it's Google makes you host stuff or where Apple makes you host stuff. Let me share it with you because it's a very useful thing and it's going to give us that perspective that I really need to do. So let me share. Let me first of all open the software in here on my computer because I have it installed. I'm going to use also a couple of other softwares at some point, probably at least Universe Sandbox. I'm going to use it. Oh man, it opened in big view. So let me minimize this. So I have Universe Sandbox, which is really more of a simulation, that one. It's really a, not a real life basically stuff. So it's based on the physics, which is important. It gives you, and then you can simulate stuff. For example, how two planets collide, how two stars collide, what happened to the sun if it happens to go supernova, for example, or Betelgeuse if it goes supernova today, how it's going to look like, and so on and so forth. And you can measure its expansion and so on. It's going to give you a real physics, but that's not this software. That's Universe Sandbox. And there is another one also called the Space Engine. Space Engine also is similar, and both of them are not free, those two, but they're useful to have if you have a powerful enough video card, because those are intended to be on gaming computers. If not, and I'm going to use probably, I have both of them, but if in case down the road, probably I'm going to use a Universe Sandbox for sure. I'm not sure about the Space Engine. Anyway, let me get into Stellarium and share it with you guys. Let me expand it a little because when you open it, it comes in full view. So you have to be careful with it. I mean, which is fine, actually. If that's the only thing you have on the computer, that's good, okay? So this is how it looks like when you open the software. It's really your time and your location. Right now, I'm in Loma Linda. It says I'm in actually I'm in Redlands, but near Loma Linda, so I guess it picks up the Loma Linda location. And it's moving with time. So I'm going to stop and pause the time right now. It's 11:20 according to this one in here. Today, September 7th of the year 2022. It uses military time thing, so it doesn't use the regular time. And it gives you more information here. One of the things you can do is change the time. And that's why it's useful actually, to see how the sky would look like, for example, 3 months from today, when I'm planning a trip to the Grand Canyon, for example. So I'll set my location to the Grand Canyon by going here, Grand Canyon. So if I start typing Grand, does it give me Grand Canyon? Grand Junction. So probably I need to put it either put the coordinates in here manually, and you can do that. So if you don't find the location, you can do it manually for the latitude and the longitude and your elevation if you happen to be on a mountain or below sea level. So right now it's taking 0 meters, which is sea level. And or basically look for the nearest city, and the nearest city, the Grand Canyon, is what? Flagstaff. Flagstaff, and it found it already. Flagstaff, North America, not Flagami. I don't know what that is. Okay. Now this is how the sky would look like in Flagstaff, which is close from the Grand Canyon. Now I'm going to change the date. I'm going to move the date in here. Are you guys looking at the stellarium or not? Just to make sure that I have you guys with me.
Yes.
Okay, very good. So I said 3 months from today, that's going to be 12. So I'm going to enter it manually, okay? And I'm going to change to the time where I can see stuff, which is somewhere around 10 p.m., for example. And as I was saying, it uses military time. So 10 p.m. is actually 22. So this is 10 p.m. and 20 minutes after midnight. And I'm looking at the direction of between south and southeast. And from the get-go, I see the Ceres, which is a big star. Ceres, when you click on it in here in the software, it gives you a lot of details on it. This is the brightest star in the night sky in terms of stars. Venus is brighter, but Venus is a planet. But so that there is a distinction. So, and it gives you all kinds of information. It gives you its magnitude. It gives you its absolute magnitude. It gives you all kinds of information about it, and including, among other things, its location, its latitude and longitude, and basically the different kind of information that you will have. Okay. So what is the J2000? Right ascension and declination. This is the numbers that you're going to be, for those sitting in the lab, you're going to be doing, but you're not tracking series. You're tracking actually, for those sitting in the lab, the next lab actually is going to be for Arcturus. So I don't know what Arcturus is, so I'm going to find it. So I'm going to come in here and put Arcturus. The minute I start typing, it's going to find that star for me. And it tells me on that day in Flagstaff, it's going to be below the horizon at 10:20 p.m. And this is a fake horizon. This is not what Flagstaff look like, if you ever have been in there, okay? But the interesting thing in here, it gives you a nice sky. This 3 stars, Ceres, Procyon, and Betelgeuse are part of what is known as the winter asterism. They form a triangle, okay? Ceres, which is part of Ursa Major, not Ursa Major, the big dog, what is that? The constellation. Canis Major, okay? Canis Major, which is the big dog of Orion, the hunter, and here is Orion. And Betelgeuse is there, and Rigel, its leg. Actually, Rigel in Arabic means the leg. That's where the word is coming from. And this is the Betelgeuse, which stands for its armpit, and it's also from the Arabic language. These 3 stars are what is known as the Orion's belt, and they're all have Arabic names. This is a Nitaq. This is actually in Arabic you don't say a Nitaq, you say a Nitaq with Kha, which is a letter that doesn't exist. This is a Nilam, and this is a Mintaqa. Again, those are the 3 stars part of the Orion's belt. And if you extend this line all the way through, the next brightest star below toward the horizon is Ceres, which is the brightest star in the night sky. And this is Lepus, the hare, and Ursa Canis Minor is here. That's where Procyon is. And those are the 2 dogs of Hunter, Orion, the hunter, and he's aiming his bow and he's pulling on the arrow, trying to shoot the Taurus, okay, which Aldebaran, which is the eye of the Taurus, okay. Actually, you can turn on something else and you can see the different figures. Now you can see clearly a Taurus. Again, those are the constellations that you have in the night sky, and this is some of the stuff that we're going to be learning about in this class. And this software is a very handy software, okay. Again, I just picked up a location, which is Flagstaff, Arizona. sitting at 2,108 meters above the level, because it knows that Flagstaff is actually way above the, because if you happen to drive toward Arizona, I don't know if you noticed that, you're always climbing, okay? Sometimes you dip, but most of the time you're climbing, okay? So overall, it's higher elevation than ours. So it's really a nice tool to have. It's free one, you can have it. And we're gonna be using it extensively in this class, so I guess you guys need to be familiar with it. It's a free one. And if you have difficulty installing the software, we meet every Tuesday in the lab at 5:35 p.m. for those taking the lab. You can bring your laptop and we can fix whatever needs to be fixed. Now, if you are not taking the lab and you still have an issue, we can meet in the office. You can bring your laptop and try to see if we can work out the details so that you will have this software, because it's really a handy, nice tool that we can have. This is in lieu of planetarium. We have a planetarium on campus and we will probably are going to visit it, but it's planetariums usually are limited by the software that they have. And most of the time they have only few shows to go around here and there, but this one goes way beyond. It gives you all kinds of things. For example, let me go back to it, share. Let me just, for example, try to find an object in here that is familiar to us. Okay, let's find Mars. Okay, it's an interesting planet. It's a nearby planet. It's showing me Mars, but on that day in that location, it's next to the moon. Okay, so on that day, this is not ideal. Actually, I chose a very bad day to go and look at them. To do night. We're really planning to go on the 7th of December, which is, we can't go anyway because we still have finals at that time. Mars will, the light from the moon will block Mars. So it's really not a good thing to do on that day. But it's nice, you can clearly see, you have the moon in here as you're zooming onto Mars. When you double click on an object, it zooms on it, but now you have all of the features of Mars that you can see, okay? And you have Deimos and you have Phobos. Those are the two moons of Mars. This is a star, okay? This is a double star, actually. So this is how you can study this object. And then let me close out. Let me first of all stop the sharing. So it gives you a lot of information, and it's a freeware, which is really a good thing to have. Okay, so this is one of the resources that I listed it in the on Canvas. So hopefully you guys will have a chance to go and explore it and use it for our class. Sounds good, guys?
Yes.
Okay, very good. So I'm going to now find my PowerPoint. First of all, Unit 5. And then share that with you guys. Share. Okay, one caution here, I know a few of you are here, is that if in case for some reason sometimes Zoom hangs, and if it does, please do not leave, okay? I'm going to restart it and then we're going to resume and the recording will resume accordingly and so on and so forth, okay? So let me share now. So again, as I was saying, the book is divided into several units. We're not going to cover the units one after the other. We're going to basically cover the topics, and they're listed actually on Canvas so that you guys know exactly what is covered and where to go from one point to what 2 points and so on and so forth, okay? So again, Unit 5 starts with the geometry in space, okay? And when you look at the night sky, when you look at the sky in general, whether at night or even during daytime, so the way you can envision it is some sort of a sphere, okay, where everything is happening on it. It's a scene where everything is happening. We call it a celestial sphere, okay? So this is a celestial sphere, and we have some, at least on campus, where you can actually represent it as a celestial sphere. And you put different dots on it, and those represent either the stars or the different positions or the path of the sun throughout the year, which we call the ecliptic, okay? It turns out that the path of the sun as it goes around the Earth every year, and you can track that down day in, day out, it's not too far from where the planets are. Two planets are always dragged by the sun. Jupiter and, Venus and Mercury, they are dragged on a regular basis by the sun. They're either leading the sun in the morning, so they're called morning stars, or lagging behind it in the evening as it sets. They set later after it, and they're called the evening stars. Especially for Venus, it's called the morning star and sometimes called the evening star, depending on the time of the month, depending on when we can see it, because it's bright. Same thing with the Mercury, but Mercury is a lot closer to the sun, so sometimes it's behind the sun and you cannot really see that. Okay, here is all of these planets. They actually orbit in the same path as the sun does, so we call that ecliptic. Okay. So we'll try to understand what's going on with that. Obviously, you know, and I know that the sun doesn't go around the Earth. It's the Earth that goes around the sun. So the ecliptic actually is a path of the Earth around the sun. And it's more or less the same plane where all of the planets move around the sun. Because of this structure, we need to understand it at some point. Why is it so? How come all of them conveniently happen to be on a plane? Why not on a big kind of every which direction? Obviously, that was a question that was bugging people, at least when they started looking at these things. The answer turned out to have very, very, very good justification, and the justification is coming from something in physics and mechanics, actually called angular momentum. So we're going to talk about that later on and try to understand how come the angular momentum fixes that understanding of the ecliptic plane, where all the planets, including the Earth, are more or less on it. Okay? The only reason why they are not exactly on it is because what happened to the solar system early on, there were too many collisions, too many drag and push and collisions with this and that, basically knocked them a little on or off of that path. Other than that, they're all on it, including now from our vantage point, when we look at the sun, we think the sun is actually moving on that path, but it's the other way around, okay? The Earth is the one. So we're going to try to describe the position of objects in the night sky, in the celestial sphere, using stuff that is familiar to us. I mentioned them earlier, the longitude and the latitude. This is what we use on Earth. We happen to be here in our area about 34 degrees north in our latitude. Basically, if you take a spherical object, and you divide it into degrees, where the equator is 0 degrees, and you go north up to the North Pole, that is 90 degrees, you don't have to go all the way to the 90 degrees. You just, by the time you reach 34 degrees, we are on the same circle that is 34 degrees above that. That puts us on a circle, as I was saying, about 34 degrees. Then we need to locate ourselves on the east-west direction, and that is actually the longitude. Our longitude is 117 degrees west. Okay, west from what? From a standard, which is the prime meridian. Okay, again, we have people by convention agreed that the longitude that passes through the city of Greenwich in England, to be of zero longitude. Zero longitude. Just as much as they agreed on the equator as being zero latitude, zero longitude sits on the city of Greenwich in England. Anything west of it has the label W west, and anything east of it has the east on its longitude. And we happen to be 117 degrees, so more than 90 degrees on the west. So we're slightly off, okay? Not completely opposite of it. If we are at 180 degrees, if Greenwich is on this side, we will be on the opposite side of Greenwich, okay? So you have to go 180 degrees. But if you continue all the way to 359.9 degrees, you will be back in Greenwich. 360 degrees will put you back where you started from. Okay, so it could be in the same city of Greenwich, you are sitting at 0 degrees, and your friend next to you sitting on actually 359.999. Okay, so that's basically, you have to go full circle, which is 360 degrees to complete that. Same thing is true for the latitude. You go from -90 degrees, which is the South Pole, and you go all the way to 0 degrees, where the equator is, and then you go another 90 degrees to go to the North Pole. We call it north 34 degrees or south 34 degrees. South 34 degrees will be a negative number. That's by convention. So we locate objects on Earth using these coordinates. In a similar fashion, we use coordinates also in the celestial sphere. We take the equator, the Earth equator, and project it in the celestial sphere. Now we have the celestial equator. We take the North Pole and we project it in the celestial sphere. That's actually where Polaris is, the star Polaris. Okay, that star is on the North Pole. Do I still have Stellarium? Because it's an interesting star to look at. So let me share with you Polaris, because it's an important thing in here. So let me share, stop sharing, and let me share now. Stellarium still has Mars in it. So now I'm going to zoom out. And let me remove this constellation because they're on the way. Okay. So this is a fake horizon. It looks like I'm looking, but now I need to look north to find where Polaris is, okay? So this is the north. This is where Polaris is, okay? Because we are at a 34-degree latitude, excuse me, it should give me the position of Polaris. Actually, it's giving me slightly more than 34 degrees, 35 degrees, okay? So Polaris is sitting, let me pull the coordinates in here. No, let me put the latitude on the line. So right now it's sitting at 0 degrees in terms of the azimuthal angle, okay? And that is actually where the north is. If you come back to it, make 360 degrees, takes you there. It takes you back in there. So this position in here in the sky, let me see if it's labeled. This is a 10 degree, 20 degree. The next line is 30 degrees. This is slightly more than, it's halfway between 30 and 40 degrees, okay? You can clearly see these positions in here on the left-hand side. I don't know if you can read it or not, but the angles is at the horizon is 0, 10, 20, 30, and then 40 degrees. So right now it's between them. So it's 34 degrees. So the way that it looks like now, this is where Polaris is. Why? Because if I'm on the North Pole and I look at Polaris, it's going to be immediately above my head. We call that the zenith. Anything you look at that is immediately above your head, it's called the zenith. Okay? So it's going to be the zenith in the North Pole. But our zenith in here is different because we are in a different location. We are at 34 degrees. Okay? Polaris is not exactly in the North Pole. It's slightly off, but not that much. Okay? So it's a good start to look at it and use it to locate yourself in the night sky, to know exactly where you are. So let me stop sharing this. It's not the brightest star, by the way. As I was saying earlier, Sirius, the one that I showed you earlier, I'm sorry, this is Flagstaff. That's another problem. That's another problem. So we probably have to find our location back again. So let's go back into our location, which is San Bernardino. And San Bernardino is giving, what is that in here? San Bernardino, North America. Yeah, that's at 34 degrees. Okay. So now we're back into San Bernardino. And where is the star itself? Yeah, it's 34 degrees. Good. Now that fixes that, okay? That fixes that. Now we're good. That fixes the problem because our location is slightly south of Flagstaff. So Flagstaff is a little bit 1 degree above us, okay? That's why the location was wrong earlier. It was kind of a liquid. Why is it 35? It should be 34. Now it's fixed. Okay. Anyway, so I'm glad that we ran into this problem, honestly. It's because when you're doing these things, sometimes you run into situations like that and you should be able to recover from them. You should be able to fix what needs to be fixed, okay? Anyway, so list points of reference astronomers use in describing locations in the sky. And we're going to talk about that, explain the daily motions of the sky and how they differ, and estimate the position of objects on the celestial sphere. Again, this is for you sitting in where you are. It looks like you are living in a dome above you. That's half of the celestial sphere, okay? That's half of the celestial sphere. Right now, I'm looking due north. I'm seeing actually the mountains of the San Bernardino Mountains. So this side in here, if I extend my arm, probably the picture is reversed because of the reflection. This side is the east. The right-hand side is the east. If I'm looking due north, this left-hand side is going to be west. Whatever is behind me is going to be the south. So if you're looking due north, then south is behind you, and so on and so forth. So you can locate objects based on these relative positions. You will have a project, by the way, and that project will be related to the motion of the moon. And at some point, you'll be asked to locate the moon. So use just this coordinate. You don't have to give me the precise coordinates. You don't have to open Stellarium and give me the location of the moon in that location. Actually, I don't need it, okay? There is a problem, though, with this whole picture, and that is an element of depth that is missing from the celestial sphere. This object that you see hanging in there, they're not at those distances. Some of them are closer than others, okay? Some of them are closer in terms of distance than others, and that cannot be represented by the celestial sphere. So there is an element in here that I cannot really do much about it. So let me stop sharing that and let me share with you again planetarium, because I need to find out these objects. I'm still looking at Polaris, and Polaris from San Bernardino right now. It doesn't matter, anywhere on Earth, it's going to give me the distance. Polaris is 432 light years away from us, very far. As opposed to Ceres, which I already looked for earlier, here, or Arcturus, okay, which is below the horizon right now, but doesn't matter, okay. If you wait a little longer, we're still at 9:20 p.m., okay. Polaris is at this, Arcturus is at distance 36 light years away. You can't do that. You can't see that. Let me move the horizon just to see what's going on. So this is Arcturus. Arcturus is actually brighter in the night sky than Polaris is. It's the fourth brightest star, and it's closer. It's only 36 light years, as opposed to Polaris, which is 400 and some odd number of light years away from us. So and the sun is only 8 minutes away from us. 8 years, 8 light minutes away from us. Okay, so it's not that far. Okay, so the element of depth in here is not properly represented on the celestial sphere. But other than that, you can locate objects based on their coordinates in the night sky. And again, the constellations, as I was saying, they're this kind of shapes that you have in the night sky. But let me show you Leo and how it looks like, so that you can actually see it. And there is a problem in here. I'm going to talk to you about it. Okay. So let's go again with the constellation names. And let's find Leo. Here is where Leo is, okay? Does this look like it's a lion to you? Well, depending on the culture, that's what they have it interpreted. Again, the shapes, the myths associated with these things depend on the culture. The Polynesian culture is not the Greek culture, is not the Romans, it's not the Arabs, it's not the Chinese, it's not the Americas. So each person has different stories associated with these different stars and so on and so forth. So please do not take it for those stories as being, oh, this is what happened to Andromeda, and this is what happened to Cassiopeia, for example, and all of the stories are just stories. It reminds me of that line from the movie The Lion King. Actually, if you saw it, when what is the kid name? The Simba, isn't it? Simba and Timon and did you guys see the movie I'm talking about? The Lion King?
Pumbaa.
Oh, Pumbaa. Okay, thank you very much. Yeah, they were sitting and looking at the night sky. I wish I can find that video and talk to you about. And they were looking exactly to what we're looking at right now. And one of them asked about these dots in the sky. What do they represent, and so on and so forth. And the answers came in 3 different fashions, and each one of them has a stories associated with it. Simba said that basically because his father told him that these are the old kings overlooking and coming to help you, and so on and so forth. Basically a story to talk about it, and he can even see shapes of his father and some other things coming at some point from this shapes in there. Timon has a different story. He says that all of those bugs, the flying bugs that they have that emit light, they're stuck in the sky, and now that they're emitting light. Okay, and it was actually Pumbaa is the one who came up with the better explanation that they're gas, basically boiling gas, extremely hot temperature, sitting at millions of kilometers away from us. So his explanation actually is closer to what we know today. Okay, of course they laughed at him, and each one of them has a story depending on his perspective and his culture or his background. And the same thing is true for the constellations. However, you need to know one thing. There is a convention now on 88 constellations. You don't need to memorize all of them. Okay, at least it's a good idea to know some of them. Ursa Major is a good constellation to know. It has this asterism, and this asterism has this spot basically, and it has a handle. Okay, and it's a good idea to recognize. The other stars are kind of faint a little bit. So what you're going to see is that this 4 stars plus this 3 for a total of 7 stars. As you follow the handle, it's going to arc. If you follow the handle of Ursa Major, the Big Dipper, this is called the Big Dipper. This is called an asterism as opposed to a constellation. Constellation is actually has a map and it has all kinds of stars in it. And but an asterism is a shape, a recognizable shape that may or may not be part of the same constellation. So like I mentioned earlier, the winter asterism, which is made up of those 3 stars, is actually an asterism, and it doesn't, all 3 stars, one of them is an Orion, the other one is Canis Major, and the other one is Canis Minor. So they are different constellation altogether. So an asterism like this one happened to be in the same constellation. But if you follow the handle of the Big Dipper, as it's arcing, and just the next brightest star is actually Arcturus. So you arc to Arcturus in this case, and you find where that bright star is, which is one of the brightest stars in the night sky. So you arc to Arcturus from Ursa Major, and then you spike to Spica, which is one of also the big interesting stars. So if you do this, you're going to start recognizing shapes in the sky. Okay, Spica is part of the Virgo constellation, whereas Arcturus is part of the Boötes constellation, which is in here. Okay, and then you have Draco, you have Ursa Minor. Ursa Minor looks like the same thing as Ursa Major, which is the Big Dipper. This is the Small Dipper, Ursa Minor. It has a handle also. Its stars are all faint. Okay, and the end of the handle is where Polaris is. So when you recognize these shapes and you go out and look for them, then you start to find stuff. This is a so-called circumpolar constellation, meaning it never leaves the sky. So if I start the time now, and if I speed up the time, you will see that all of the constellations starts to move. Why? Because the Earth is spinning. But look at this. It stays because Polaris is still there, even if I put the horizon back. So stars are coming in and out of, or constellations are coming in and out of the horizon, except that this ones, they spin and stay all the time in the sky. So one of them is this one. One of the constellation is this one. Let me zoom out a little bit to find the other one that is famous actually. Cassiopeia. Where is Cassiopeia right now? Let me remove the here it is. Okay, so let me zoom back on it. And right now it looks like it's a W. When it moves back, it's going to be a backward 3. Then when it's in the night sky, it's going to be more of an M. Then it's going to be a 3 and a W. And again, it's going to move around. Okay, wait for an hour and you're going to see it shift by about 15 degrees in the night sky. And it's true for all of this thing. So these are so-called circumpolar constellations. And there are stars also that are circumpolar, meaning that they move around the Polaris, which is the northern star. That's the one that doesn't move. So if they speed up the time, you will see everything moving actually at a higher speed, okay? So these are circumpolar constellations, as opposed to, let me pause, stop the time, as opposed to zodiacal constellations. Those are constellations that follow the sign of the zodiac, okay? And there are 13 of them, okay? There is a 13th constellation actually, and those are the Cancer, Leo, and all of these things, the Pisces and all of the other constellations. And they depend on the time of the year, because as the Earth is moving around the sun will hide the ones that we saw 6 months ago, because we have to see them during daytime. The only one that's possible is if there is a solar eclipse. Then we will see those constellations that we saw 6 months ago during daytime on the same side of the sun. But the ones that were hidden by the sun 6 months ago, now they are actually in our night sky. So as the sun follows, those are the signs of the zodiac. The reason why I'm saying it's 13 is because there is a gap between two constellations where there is a 13th constellation sits in there, but because we conveniently define the year as being 12 months, so we only have 12 constellations as part of the signs of the zodiac. And then you have the seasonal constellations. Those are constellations that show during some times of the year and other times do not show, and they are not circumpolar and they are not part of the sign of the zodiac. In other words, the ecliptic does not pass through them. So those are the different constellations that you have. You don't have to memorize them, as I said, but it's good to know some of them. One of them that we talked about earlier, which is an important constellation, is Orion. It's a very useful constellation. I mean, if you can recognize it right away from its belt, okay? Betelgeuse, which is a big star, and it's, let me pause the time because the time is moving. I don't like these things moving around right now. It gives you its distance to from Earth, and its distance from Earth should be a few hundred light years, about 400 or 500 light years away from us. What is the distance? Period, separation. That's odd. I don't see the difference unless. It should be part of the stuff that we have, because Betelgeuse is a big star. And it's a star that we're expecting to go. Here is the distance, about 500 light years away from us. Okay. Rigel is the opposite star to it. It's also part of the same constellation. Let me remove this thing for a moment in here. This is Saif, which is the Arabic word for actually a sword. But this is actually the sword of Orion. This is what is known as its sword, and it's part of this stellar nebula that has a lot of stars forming in that region in there. And this is Bellatrix, and those are the major stars in this constellation. So from it, you can recognize so many of the things. If you straight this line on the belt, the next biggest, brightest star, and it's the brightest star in the night sky altogether, it's Ceres, okay? So that is the brightest star. So it gives you all kinds of information on these objects in here. So knowing constellations and where they are, it's a useful thing to know, because it helps you, especially with asterism. Like, for example, I was talking about asterism. This is a line that you can recognize in the night sky. There's 3 stars. And it helps you immediately find the other 2 major stars, or 3 major stars of actually Orion. And then extend these lines, and now you have a series. Ceres, Betelgeuse, and Procyon, they're part of the winter asterism, which is a triangle. And as I was saying, they don't necessarily belong to the same constellation. Each and every one of them is actually on a different constellation altogether. Gemini is part of the signs of the zodiac. So if I click the comma line, the comma in here shows me the ecliptic. And in here, this line passes through all of the signs of the zodiac. So of course we have Gemini, we have the Taurus, we have the Pisces, we have Aquarius, we have Capricornus, we have Sagittarius, we have, this is the 13th constellation, okay? Because the Scorpion or Scorpius and Sagittarius are two constellations of the signs of the zodiac, and the space between them is big enough so that this, I think they call it Ophiuchus, is the 13th sign of the zodiac. And if you continue, you have Libra, you have Virgo, and you continue all the way to Leo, the lion, Cancer, Gemini. We're back into the starting point, okay? So there are 12 of them. And some of them appear, some of them don't appear. Those are called the seasonal constellations, okay? So let me stop sharing that and let me go back into my notes, share. So again, the shapes depend on the culture, the way they look also depend on the culture and so on and so forth. This is Cygnus, which is another constellation in the night sky, but it's a good idea to recognize some of the common shapes, as I was saying. The coordinates on the celestial sphere are, again, you extend the equator of the Earth to the so-called celestial equator, and the North Pole from the Earth to the North celestial pole, and the South Pole on the Earth to the South celestial pole, and you start calling whatever it was latitude before is going to correspond to something called the declination on the celestial sphere. Whatever it was longitude on Earth now is going to correspond to something called the right ascension on the celestial sphere. One more thing in here, the right ascension is measured in hours and minutes and seconds, versus the declination, which is measured actually in degrees and arc minutes and arc seconds. So those are the two things. What is immediately above your head is called the zenith, and it's coming from the Arabic word, which is the tip of the head. The nadir or nadir is actually the opposite. That's actually coming from the Arabic word also, which stands for the opposite, okay? So those are the two terminologies that we use in terms of the positions in the night sky, okay? Again, if you move around, your celestial sphere changes because your horizon changes, or at least your dome changes, because your horizon changes and your nadir and your nadir at the bottom and zenith at the top will change, okay? I know it's long and I know kind of tiring, but I'm hoping that to finish this at least in the next, we're supposed to go all the way to 12:10. So give me about a few minutes and then we'll finish this. Again, the coordinates on the Earth, we use the longitude going east-west. The longitude going east-west and the latitude going north-south, and they are both in degrees. With respect to the prime meridian, and the prime meridian, as I said before, goes through the city of Greenwich. And the 0 degrees for the latitude goes through the equator. If we take that and project them on the celestial sphere, we will find again the declination where 0 degrees is actually the celestial equator. Anything above the 0 degrees is actually a positive value of declination. Anything on the opposite direction is a negative value, as you can clearly see. The right ascension is basically the equivalent of east-west, taking a convention of when to start putting them, and then it starts from 0 hours all the way to basically back to 24 hours. So instead of measuring it in degrees, we measure it in hours. And then the fraction of an hour is a minute, and the fraction of a minute, which is 60 minutes, make an hour, and 60 seconds make a minute, okay? So this is your first unit. I should have the recording available to you guys soon, okay? And hopefully you guys will watch it in there. Any questions? Okay, if not, then I will guys see you next week Monday, the same time, okay? And I promise we will have problems to do, and with the problems, actually, the learning will happen a little bit better. Because when you have things to do, it's more much easier for you guys to catch concepts. And the other thing, you have discussions and you have introduction of yourself, and you have a lot of things to do this week. So please do not forget those assignments. They're due, one of them is due actually next Wednesday, and the other one is due the weekend after. So please take care of those as soon as possible. Thank you, and please, and I will follow up with messages to you guys. Thank you, guys.
Thank you.
Thank you.
Bye.